Hi everyone, my name is Zwaan. Welcome to my presentation about the mapping and modeling of a future passive margin in Afar in East Africa. This presentation is based on two publications from last year in Tectonics and Tectonophysics. This is part of a project funded by the Swiss National Science Foundation. And this project was also a collaboration between the University of Florence in Italy, the Italian National Research Council, the University of Southampton from the UK, Addis Ababa University from Ethiopia, and Victoria University, Wellington from New Zealand. I would also like to thank the organization of this Australian Earth Sciences Convention for having me as a keynote speaker. It's a great honor. And now I would like to introduce you to Afar. So Afar, shown here on this map, is a depression in East Africa, which has a triangular shape between the Nubian plate to the west, the Danakil block to the northeast, and the Somalian plate to the south. It's also a part of the East African rift system, which comes in from the south in the shape of the main Ethiopian rift, and then forms a triple junction with the Gulf of Aden to the east and the Red Sea to the north. It's an area which is prone to volcanism, and it's an active continental breakup zone. It's unique around the world, and it's a perfect place for the study of rifting processes. Now, since Afar is breaking up at the moment, it's also developing passive margins. For instance, the Southern Afar Margin to the south and the Western Afar Margin to the west. And we are interested in the Western Afar Margin, which is characterized by something we call flexure, as shown on this section over here. We go from the Ethiopian Plateau to the west to Afar in the east. And this flexure is characterized by an escarpment fault, so a first step downward, and then antithetic faults dipping towards the plateau. And in between of that, we have a marginal graben, which is a little graben hugging the margin, if you want, and which is often well expressed in the topography. A problem with this Western Afar Margin is that it's really not well understood, and a lot of people have contrasting ideas about how this Western Afar Margin has formed. You can see an overview, you can find an overview in our review paper in the Journal of African Earth Sciences. But the big problem is really that we don't have sufficient data to really make a choice. So the goal of this project was to study the margin and to find more structural data and to characterize the tectonics of the margin. We use different methods, such as earthquake analysis, interpretation of faults on a large scale by means of satellite data and digital elevation models. And after that, we went into the field to collect data on faults and geomorphology. And with all that information, we also devised analog models to better understand the dynamics of the whole system. So let's start with the structural analysis. What is shown here is the earthquake analysis and a map of all the earthquakes from the sources shown here to the right. And what you can see is that you have the rift axis in Afar quite clearly visible. However, the Western Afar Margin itself is also quite active. So it's not yet a passive margin, it's still an active rifting margin. And these earthquakes we can use to characterize the type of deformation going on. So what you have here are the focal mechanisms, and you can derive the t-axis from that, which then are shown on this map over here. And if you group these t-axes in certain areas, like the Western Afar Margin or the Afar Depression or the main Ethiopian rift to the south, you can derive a general extension direction. So for instance, the Western Afar Margin has an extension direction which is almost east-west, whereas the extension direction in Afar itself, it's a bit more southwest northeast, and the main Ethiopian rift has then again a bit more northwest southeast extension at the moment. The next step was to do the large-scale structural interpretation of the margin, as shown here to the right. So this is the northern part of the margin, and this is the southern part of the margin. All the the white lines are the faults. These can be synthetic or antithetic faults, so either dipping towards Afar or away from Afar. We find, of course, the plateau. We have these marginal grabens and the different faults. And this structure that we find from the mapping exercise, it's really quite well fits with the earlier idea of what the structure is of this margin. So that's a good fit there. What we also found is that the orientation of the faults and the structures along the margin is dominantly north-northwest, south-southeast, as shown in this histogram here and also on this map. And since the margin is north-south, that means that we have an on-echelon right-stepping arrangement of our structures, of our faults, of our escarpment faults, of our grabens. And this is important later on. After this large-scale mapping exercise, we also went into the field to ground truth the faults and to also measure the faults to get an idea of what's going on. What you can see is here is that we are enjoying the local cuisine, so injera and tips, which are local delicacies. And to the top here, we were at the Ethiopian Plateau, which is a really rich agricultural area where lots of people are living. By contrast, Afar itself is a barren wasteland. As you can see here, these are just basalt flows. It's dark, nothing is growing. There's a large shield volcano in the background, and that area often gets well up to 40, 50, or even 60 degrees Celsius. It's really a really tough area, a tough region to work, to live, but still people are around there. And of course, next to all the tourism, we also had to do some work. So as you can see, we were busy measuring the faults in the field. With this fault information, we created an analysis of the extension direction associated with these faults by means of the program wind tensor. And what we find is that the extension direction is dominantly east-west. By the way, we also use data from previous fieldworks to create the first ever characterization along the whole of the Western Afar Margin. And if we put this now in a regional context, we can plot the t-axis, we can plot our fault data or the extension directions from our fault data, and we can also put some GPS data in there. And this all really nicely fits with the rotational opening of Afar at the moment due to the rotation of this Danakil block, which is rotating about a rotation axis somewhere here north of the Gulf of Zula. There is, however, a question whether this has been the case for all of the history of the Western Afar Margin, since this rotation of the Danakil block is supposed to have started some 10 or 11 million years ago, whereas we do know that Afar has been developing since about 25 million years ago. So now if we look at the large-scale tectonic situation in the area, we should expect that the rotation of Arabia, which is affecting the Red Sea and the Gulf of Aden, should cause a oblique extension, a sinistral oblique extension along the north-south oriented Western Afar Margin. And there is some evidence for this as well. We find this on-echelon arrangement along this Western Afar Margin, and there is also field data from Corrix et al. That suggests a similar extension or even strike-slip motion along the Western Afar Margin. So there's a problem. We have this current near orthogonal extension with respect to the margin, and the solution that we have for this is that there had to be some multiphase rotational rifting. So first, during the first phase, we have Arabia rotating and the Western Afar Margin being subjected to oblique extension. And then in the current phase, after the individual rotation of the Danakil block, the Western Afar Margin started to undergo more or less orthogonal extension. This can be captured in a larger map, as shown over here, with the first phase and the rotation of Arabia causing, again, oblique extension, and the second phase involving the rotation of the Danakil block on a smaller scale, causing orthogonal extension more or less along the Western Afar Margin. Now with this, we have a general idea of the regional tectonics and the effects it had on the extension directions along the Western Afar Margin and the large-scale structures. However, we would like to know a bit more into detail what the dynamics were of the development of the margin and how this has affected the smaller, the more detailed structures. So for this, we moved to analog modeling. And we start with the idea that the subsidence of Afar with respect to the plateau has created this flexure, and the typical structures involving and this escarpment fault, the enthetic faults, and also the marginal graben, so typical for the Western Afar Margin. Now, we designed a model setup in the University of Florence Tectonic modeling lab. And this model has layering, which is so-called brittle viscous, in which we have a top layer of sand representing the upper crust, the brittle upper crust. And then below that, well, viscous material representing the lower crust, the ductile lower crust in nature. We have a strong lower crust representing the Ethiopian Plateau, and a weak lower crust representing the low crust in Afar, because that is weakened by constant magmatism below the rift. And on top of that, we have a little intercrustal layer, which allows a bit more flexure of the whole system. Below all of that, we have a very weak layer. This layer allows deformation of the top layers. This is a model necessity. And extension is applied by removing one of these spaces here, which then allows space for this internal sidewall to move in this direction. And it's forced to move in this direction by applying enhanced gravity. So what we do is that we put the model into a centrifuge machine together with a counterweight. We start then rotating them, and the rotation or the centrifugal force creates up to 20 G. And this force then forces the model to extend and to fill up the space that was left by the spacer. Now, we can take top view pictures at every time step, and then we can make a time-lapse video of that. And what you do see is that we have to the left here the plateau, and to the right we have then the model Afar with the Western Afar Margin and an escarpment fault, a marginal graben kind of structure, and also lots of smaller faults over here. So that seems to work quite nicely. And this is another model. We can also take side view pictures where you can again see something like a plateau, Afar, and a zone of flexure where we have an escarpment, a marginal graben, and we also have enthetic faulting. So these side views and pictures from different directions allow us also to recreate the topography of these models as shown over here. So we start with a flat model topography, and then we keep on deforming, and we create a plateau, a depression, and a margin. And these topographic data allow us also to create profiles and to trace the evolution of these profiles, or of the topography along these profiles. As you can see here, you have increasing subsidence and different structures developing, which is really useful. And we can also, at the end of the model, we can make sections by wetting the sand, then freezing the whole model, and then cutting it. Now, if we put it all together, the flexure seen in 2D really nicely explain how the Western Afar Margin developed. So shown here to the right, we can see how flexure, at increasing steps, develops first an escarpment fault, and then later on the marginal grabens and the enthetic faults. This means that the escarpment fault is quite an important part of the system, and the marginal grabens and the enthetic faults, which are, however, still very typical of the Western Afar Margin, are later and a bit more minor structures. So now with these models, we have, at least in 2D, an understanding of how flexure can create the structures typical for the Western Afar Margin, with the escarpment fault developing earlier and the marginal grabens developing later. However, this is only in 2D, and we have seen already from the other data that the evolution of the Western Afar Margin involved 2 phases of extension. So therefore, we went and tried to model these two phases as well. So what you see here to the left is a model that represents the first phase of extension, where we have a strong lower crust and a weak lower crust like before. But the limit between these two domains is now oblique, so that if we move the sidewall apart, the extension will be oblique. And what happens then is that we create offset faults, on-echelon offset fault, right stepping, like the large-scale structures along the Western Afar Margin. And importantly, we don't really see any marginal grabens developing. It's not possible to then take this model and do a second phase with a different extension direction in the centrifuge. So therefore, we had to develop another model to reproduce the second phase, which then involves again a strong lower crust and a weak lower crust. However, here in the separation between the two domains has a couple of steps, like indicated by this dotted line over here. And if we then apply extension to this model, then we create on echelon offset marginal grabens. So the idea is then, of course, that the on echelon structure from the first phase is inherited in the form of this boundary between both domains. Now, with the structural analysis done and also the analog modeling complete, we can bring everything together in order to have a complete scenario for the evolution of the Western Afar Margin. So as a conclusion, we can say we need the two-phase extension and the marginal flexure to explain the evolution of the Western Afar Margin, which is illustrated in this figure here, where we first start with the rotation of the Arabian plate, causing oblique extension along the Western Afar Margin. And this oblique extension causes the development of an on-echelon escarpment fault, shown over here. And then during the second phase, when the Danakil block started rotating independently, instead of oblique extension, we create orthogonal extension or near orthogonal extension, which then creates more flexure and allows the development of the marginal grabens and antithetic faults. However, these structures, they formed along the previously developed escarpment, so that we still have this on echelon arrangement of marginal grabens and antithetic faults. So this is the new model that we propose for the Western Afar Margin. We can try to use this model to better understand the evolution of other passive margins. In this context, it's important to realize that flexure is quite a typical feature of magma-rich margins. So rift systems that have a lot of magmatism going on during breakup. And unfortunately, I cannot show you the relevant images due to copyright limitations, but also on seismic sections, we often see these antithetic faults. We see the flexure. However, the marginal grabens are often not really developed or absent. And this might just be simply due to the fact that marginal grabens have a difficult time developing under oblique extension, whereas oblique extension is quite typical to occur during the evolution of a rift system. And the other factor might also be that Afar and the Ethiopian Plateau have quite high difference in elevation at the moment. And so it might be, as we've seen in our models, that you need quite a relative substance to even create marginal grabens. So we can say that our results have important implications for the understanding of passive margin evolution in general, and especially magma-rich passive margins. I would like to thank you for your attention, and I would be happy to answer any questions during the Q&A at the end of the session. And of course, you can also send me an email to contact me with more detailed questions. Thank you very much.